Hello there. In the last couple of videos, we introduced the concept of a moment generating function for a discrete random variable. In this video, we'll look at the moment generating function for a particular discrete random variable, namely the geometric random variable. So recall, firstly, that the moment generating function for a random variable x of parameter t is equal to the expectation of the random variable e to the tx, which by the Taylor series of the exponential function is equal to the summation from k is equal to 0 to infinity of k, what do we have here? That would be t to the k divided by k factorial times the expectation of x to the k, and this is also equal to the sum across all x values for the distribution of e to the tx times p of x. So let us assume that x is a particular distribution. So let us assume x follows a geometric pattern. So let's assume x is a geometric random variable. So if x is a geometric random variable, then that means the probability mass function for x is going to be equal to 1 minus p to the x minus 1 times p, where p is the probability of success. Remember, p is always a number between 0 and 1, let's assume, and also the support of the function p is any number in the interval 1 to infinity. Alright, so with this information, let us generate the moment generating function for p of x. So if this is true, mx of t, by definition is the expectation of e to the tx, which from the definition is going to be equal to the sum across all x in the domain of p of e to the tx times the probability of x. So if that is true, well, the support of x is going to be 1 to infinity, so that would be our sum values. So the sum must range from x is equal to 1 to infinity of e to the tx times the probability mass function of a random variable, which is 1 minus p to the x minus 1 times p. So just a couple things here. I'm going to factor out my p out of my summation since it is a constant, and I'm going to rewrite this exponential term using the property of a to the x minus y is going to be equal to a to the x divided by a to the y. Alright, so once I use those properties and factor out the p, I'm going to have that this is equal to p times the summation from x is equal to 1 to infinity of e to the tx times 1 minus p to the x divided by 1 minus p. My 1 over 1 minus p is also constant, so I can factor that out. So I can rewrite this instead as mx of t is equal to p over 1 minus p times the summation from x is equal to 1 to infinity of e to the tx times 1 minus p to the x. Notice that both of these terms here all have an x in the exponent, so I can take advantage of the property that ab to the x is the same as a to the x times b to the x. So once I implement that property, then I have mx of t is equal to p over 1 minus p times the summation from x is equal to 1 to infinity of et 1 minus p all raised to the x. Now notice that this summation almost resembles a geometric series. Remember, a geometric series has the structure k is equal to 0 to the infinity of a to the k, which converges as long as the absolute value of a is less than 1. But there's a big issue here because this starts at 1, that starts at 0. So what we can do is we can add 1 and subtract 1 to this expression, because when x is equal to 0, this expression is equal to 1. So since we need to introduce one term, I'm going to subtract 1 and add 1 to my expression. So mx of t is going to be equal to p over 1 minus p times, and then I'm going to have negative 1 plus my series, so x is equal to 1 to infinity of e to the t 1 minus p all raised to the x Now, since this is my 0 term for x, I can combine these into a sum that starts at 0 and goes to infinity. So I can rewrite this as m sub x of t is equal to p over 1 minus p times negative 1 plus the sum from x is equal to 0 to infinity now of e to the t 1 minus p all raised to the x. Alright, so this is a geometric series and converges to, so if we call that u, that converges to 1 over 1 minus u as long as the absolute value of u is less than 1. So that means mx of t is equal to p over 1 minus p times negative 1 plus 1 divided by 1 minus that expression, e to the t 1 minus p. And this is true if the absolute value of e to the t 1 minus p is less than 1. Let's do some simplification. I can combine these fractions, negative 1 over 1. So I have m sub x of t equals p over 1 minus p. So get a common denominator, so I'm going to multiply top and bottom of that expression by that. So I'm going to have negative 1 plus e to the t 1 minus p. I'm changing my signs because that's a negative 1. And then I have plus 1 from the numerator of that fraction all over the common denominator of 1 minus e to the t 1 minus p. So what do I have? So I have minus 1 plus 1. Those will cancel. I also have 1 minus p, 1 minus p. Those will cancel as well. So that means mx of t is equal to p e to the t all over 1 minus e to the t 1 minus p. And this is true if e to the t 1 minus p is less than 1. And I can drop my absolute value bars because e to the t is an exponential function, always positive. But sometimes it's always positive, so I can drop the absolute value bars. And 1 minus p is always less than 1 as long as p is not equal to 0. Alright, so do we really care about this restriction? So remember, for the moment generating function, we're going to be plugging in 0 into this expression. So it is, if t is equal to 0, e to the 0 times 1 minus p is going to just be 1 minus p. This is always less than 1, as long as p is not equal to 0. So this criteria is okay for our situation. So this expression is our moment generating function. To make this a little bit more practical for differentiation, what I'm going to do is multiply top and bottom by e to the minus t. That's going to cancel two of these exponentials and only have one other exponential in this expression. So I can rewrite this as mx of t is equal to p divided by e to the minus t minus, parentheses, 1 minus p. I can distribute my minus signs in there, so I have that m sub x of t is equal to p over, so we have p minus 1 plus e to the minus t. And this is true for t is equal to 0. We've already verified that. So what I'm going to do is I'm going to bring this up and write it as a negative first power, and you'll see why I want to do this in a minute. So I have mx of t is going to be equal to p times p minus 1 plus e to the minus t all raised to the negative first. So this is my moment generating function for a geometric random variable, and I have it set up in such a way such that I'm ready to take derivatives of it very quickly. So I'm not going to verify this here, but one can show that mx of 0 is equal to 1. And that's a very good property, or it's a necessary property for probability distributions. So what about the first derivative of this function? So m prime of t. So we're going to bring down our negative 1. So we have negative 1 times p minus 1 plus e to the minus t raised to the minus 2 times the derivative of the inside, which is negative 1, e to the minus t. My negative and negative turn to a positive. So m prime x of t is equal to pe minus t, p minus 1 plus e minus t minus 2. So now that I have my first derivative of my moment generating function, I can find the first moment of my random variable. So that is equivalent to finding m prime of x of 0. So that's going to be equal to p times, well, any exponential is going to go to 1. So that's going to be 1 times p minus 1 plus 1 raised to the minus 2. Which is p times, so minus 1 plus 1 is 0. We have p to the minus 2, which is the same as 1 divided by p. So that means the mean of a geometric random variable is 1 over p. So that proves that. So now let's find the second derivative of our moment generating function. So that means we need to take the derivative of this expression, which is going to require a product rule. So that's going to be equal to the first times the derivative of the second. So that's going to be minus 2p minus 1 plus e to the minus t minus 3 times minus e minus t plus the second p minus 1 plus e minus t minus 2 times the derivative of the first, which is going to be minus p e minus t. So that's a product rule going on. Now let's rewrite this in a nicer way. So m double prime of x of t equals, so what do we have here? So we have that term and that term, so we have a, what is that, a negative p e to the minus 2t. Oh, we also have a negative 2 there, right? Very easy to miss him. So let's see, we have 2p e to the minus 2t times p minus 1 plus e minus t, all raised to the minus third. And then we have minus p e to the minus t times p minus 1 plus e minus t minus 2. So now that we have our second derivative here, now finding the third derivative would be a good exercise for those who are wants a challenge. So my second moment is equivalent to finding m double prime of x of 0. So all my exponentials are going to go to 1. So that's going to give me 2p times, so that's 1, that's minus 1, so they're going to cancel, so I'm going to have p to the minus 3 minus p times, again, that's going to go to 1, that's minus 1, they cancel. I have p to the minus 2. So I have ex squared is equal to, so we have 2p over p cubed minus p over p squared, which is 2 divided by p squared minus 1 over p. I'm going to get a common denominator here and multiply top and bottom by p, or I could have kept that original expression, and that's just going to give me 2 minus p over p squared. So that is the second moment of my random variable. So now that I have my second moment, and I also have my first moment, I can find the variance. So we have that the variance of a geometric random variable, as we know, is equal to the second moment minus the first moment squared. So the second moment is equal to 2 minus p over p squared. The first moment is 1 over p, square that. We have this is 2 minus p over p squared minus 1 over p squared, and 2 minus 1 is equal to 1, which gives us 1 minus p over p squared. So what have we shown? So we've shown that if x is geometric, then its moment generating function mx of t is equal to p e to the t all over 1 minus e to the t, 1 minus p, and we've used it to verify a couple things. The first moment is equal to 1 divided by p. The second moment is equal to 2 minus p over p squared, and from both of them we used it to prove that the variance of x is equal to 1 minus p over p squared. And we used the moment generating function to generate all these results.